I'd like to welcome you. I'm Jonathan Hirsch, and I'm a development manager and engineer here at Bentley. And today I'm going to be talking about vibration of concrete floors, and particularly vibrations caused by footsteps or footfall. So let's jump right in. Just a quick outline of what we're going to go over today. We're going to look at some basic vibration theory and terminology that will be useful for the rest of the presentation. We'll take a look at how we calculate the vibration response of irregular concrete floors. And then we'll take a look at how we evaluate sensitivity criteria. When do we know if vibrations are within acceptable limits? And we'll look at that from the perspective of both occupants and sensitive equipment. We'll discuss what resonant and impulsive responses are to footsteps and how we calculate them. And then lastly, we'll take a look at what effect post-tensioning has on vibrations. Every structure has natural tendencies in the way it tends to vibrate, and it's an inherent property of the structure, just like concrete strength or density. If we look in the lower left-hand corner, you'll see a formula for natural frequency. This is for a simple single degree of freedom system, but I wanted to point out the relationship between natural frequency and stiffness and mass. So you'll see that natural frequency is generally proportional to the stiffness and inversely proportional to the mass. We can also calculate natural frequencies for more complex systems. Even a simply supported beam has many natural frequencies and mode shapes. The natural frequency is just the frequency at which it oscillates, and the mode shapes are the deformation shapes that correspond to each particular mode of vibration. So you'll see here for a simply supported beam, we're showing three different mode shapes. Mode shapes are actually unitless, and they're often normalized. So two ways in which mode shapes are typically normalized are unity-based, where the maximum value in the mode shape is set to be equal to 1, and mass normalization, where the mode shapes are normalized in such a way that the mass matrix entries are all equal to 1. When we're looking at floor vibrations, we're typically interested in vertical degrees of freedom. So we're looking at these up and down motions like we're looking at in these simply supported beams. If we were looking at seismic, we might be interested in horizontal degrees of freedom and horizontal mass and entire building movements like the one we see up in the upper right-hand corner there. So every structure has many natural frequencies, and the fundamental frequency is simply the smallest natural frequency and associated mode shape. For those of you who took structural dynamics, you'll remember that we can solve for these natural frequencies and mode shapes in complex structures by solving the eigenproblem. So we solve for the eigenvectors, which represent the mode shapes, and the eigenvalues, which give us the natural frequencies. Let's turn our attention for a minute to dynamic loadings. Dynamic loadings differ from static loadings in that static loadings tend to cause the structure to deform, but not necessarily to vibrate. So dynamic loadings are variable in nature, and they can often be expressed as a fraction of the static load. But as you can see, there's a few different ways here we can describe these variable dynamic loadings. The first one is a harmonic loading, which is a pure sinusoidal loading. One example of that here would be the blue line here in the chart. And a practical example of what could cause this would be a piece of machinery that's oscillating at a particular frequency and can cause very predictable sinusoidal loadings. So that's a harmonic load. Another type of dynamic loading is a periodic loading. An example of that would be the red line in the diagram here. And this type of load is repeating, but it's not sinusoidal, so it is repetitive from cycle to cycle. And then the next type of load we'll look at is a transient load, and this type of load is generally continuous, but it may or may not be repetitive. One example of this is an actual footstep. So footsteps are repetitive in that they occur one after another, but each footstep could be slightly different. So no two cycles are exactly the same. So we have a continuously applied load that may be fairly random or variable in nature, or it may be somewhat repetitive, but not repetitive enough to be called periodic. The last type of load we'll look at is called an impulsive load. This is a high force applied over a short period of time. So one example of this is a footstep, an individual footstep, or a heel drop. Let's take a closer look at the red curve, which, as I said, is the design footfall curve that we're going to use in our implementation in this presentation. So this curve was actually constructed from a series of measured footfalls. So they measured a large number of footfalls, studied the patterns, and then created this design curve, which was meant to represent a curve with a minimal probability of exceedance. So a reasonable expected design footfall. We can see that when we look at our closed form solutions later, we'll see that we don't have any way to solve for such a variable curve. So what we can do is deconstruct that curve into a set of harmonic sinusoidal loads that we can use in combination to create the red curve. So the summation of the other four curves that we show there, the blue dotted line, the green dotted line, the orange dotted line, the magenta dotted line, the summation of those represents our design curve. And we do have closed form solutions for harmonic curves, so that's the convenience there. You'll notice that we have four different harmonics that we use to construct this curve, and they are decreasing in magnitude. And I'm going to introduce now the term dynamic load factor, which is a factor that's applied to the static load to come up and adjust the magnitude of the individual harmonic load. So by adjusting the dynamic load factor for each harmonic, we can get the shape of the red curve we desire by combining the characteristics of the individual harmonic curves. One other thing to point out is that the higher the harmonic number, the less influence it has on the design curve. So you'll see that the first harmonic, which is the blue curve, has the biggest influence, while the fourth harmonic, which is the orange curve, has the smallest influence. This also naturally implies that the first harmonic has the largest dynamic load factor, and the dynamic load factors decrease as we increase harmonic number. The next term I'll introduce is damping. So damping is an energy absorbing mechanism that dissipates vibration. So if we look at the curve on the left hand side, that's what we call free vibration, which means there is no damping. So basically this will continue to vibrate and oscillate without any loss in amplitude. Whereas if damping is applied, we get some energy dissipation that causes a degradation of the amplitude. If we look at the red curve on the right, which is called an underdamped situation, simply means it's still oscillating, but we have some loss in amplitude in each cycle. And you can see how the amplitude gets smaller as the time goes on, but we still have multiple cycles, so we still have oscillation and vibration. This is using viscous damping, which is just a mathematical model to represent damping. There are several available. The ones we're going to use in our implementation are viscous damping, which is analogous to a friction in a fluid that is proportional to the velocity. So we get some loss in energy that's proportional to the velocity of vibration. And a practical example of this is a shock absorber in a car. One other term that I want to introduce is critically damped, and that is the blue curve on the right. And that is just the level of damping that's necessary to prevent oscillation altogether. So that you see that blue curve touches the y-axis right as it reaches one cycle. So that's called critically damped. And that's important because we often express our damping in structures as a percentage of critical damping. So these are some recommended values to be used in structures. And again, this is going to be expressed as a percentage of critical damping. You can see that structures, just by their nature and the materials, have some inherent ability to damp vibrations, usually small, in the neighborhood of 1% or so. So typical values you might use in a day-to-day design situation would range from 1% up to 4.5%, depending upon the amount of fit out you have in the structure, and also whether or not you have full height partitions, which tend to dissipate vibrations and cause damping. So if you have extensive fit out and full height partitions, you might be in the closer to 4 to 4.5% of critical damping. And so these will be an input values in the implementation that we use. The source of this table is from the design guide. I mentioned it in the last slide. The implementation that we use in RAM Concept and that we're going to show in this presentation today is outlined in this design guide. And so the reference is here, and I recommend anyone who's interested in learning more about vibrations and specifically RAM Concept's implementation for vibration, get this guide and read it. There's a lot of valuable information there. Okay, at this point we'll start talking about the solution of the dynamic system. And if you look in any dynamics text, you'll probably see a diagram similar to this one where it shows the classical single degree of freedom system, where the degree of freedom is in the direction U there, and you have a mass that's on rollers on a frictionless surface, and then you've got a spring tied back to a fixed wall with stiffness K, and then you also have a viscous damper in there with damping property C. And we're applying a sinusoidal load to this mass that has the same frequency as the natural frequency of the system. And that's important because when you apply a load that matches the natural frequency of the system, you get a buildup of response called resonance. And if left unchecked, the response would just continue to increase to infinity. But when you have damping involved, that tends to dissipate some of the energy. So if you look at the diagram in the upper right, you'll see that we're plotting three different conditions for this case where we have three different damping properties. The first one is 2% of critical damping, which is the blue color there. And then we've got 5% of critical damping, which is the green. And then the magenta is 10% of critical damping. And what you'll see is that after a number of cycles, particularly with the higher damping levels, it reaches sort of a peak response. And this response is called steady state. And it can be described with the equation in the lower right-hand corner, where the P is the dynamic load and the zeta there is the damping properties as a percentage of critical damping. But you can see that the time it takes to reach steady state as well as the total steady state amplitude is heavily dependent upon the damping itself. I want to introduce the concept of modal mass. So modal mass is the amount of mass of an equivalent single degree of freedom system. So for a complex system, it's how we could represent it in a single degree of freedom system and get the correct mass value. In essence, it's the amount of mass participating in a particular mode. So each mode has its own modal mass. You can see the equation there for modal mass where J is the mode number, I is the location in the floor. So we basically sum for each location in the floor the mass at that location times the mode shape value squared, and that's a unity normalized mode shape value. So we take the mode shape at each location, square it, multiply it by the mass, and sum that over the entire floor, and that gives us the modal mass per that floor. If we look at that value for the simply supported beams we looked at in one of the first slides, we've got the first three modes shown here, and you can see that the modal mass for each of those is half. So half of the mass, if you were to replace the simply supported beam with a single degree of freedom system, you would use half of the mass, total mass of the beam. You can see we can see a modal mass for every mode that's calculated. So if you look in the table to the right there, you can see the modal mass that's calculated for each mode, and then we also show a modal mass fraction, which is the modal mass that's calculated over the total mass in the floor. You can see that by the time we get up to mode 6, we get into some modal masses that are a little bit smaller. Those get into some torsional modes where the beam is twisting as opposed to just pure up and down motion. I want to point out one more thing. A low modal mass doesn't necessarily mean that that particular mode is not going to be important in the dynamic calculation. It really depends upon where you're applying the excitation and where you're going to be calculating the response. A small modal mass could mean that only a small portion of the structure is active in that particular mode, but if that's the area you're interested in calculating vibration for, then that could still be very significant in the calculations. At this point, I'm going to start talking about how we actually quantify vibrations. And first, we're going to talk about a resonant response. And if you recall, that the resonant response is a buildup of the response from cycle to cycle such that it increases. And if you recall from a couple slides ago, when we were looking at the single degree of freedom system, when we have damping, we expect it to reach some steady state, which is our maximum acceleration. And that formula is shown here on the top left, on the left side of the red bar. And it really just involves the dynamic load, the damping fraction, and the mass. And so that's a very simple closed form solution, but it only applies to the single degree of freedom system. Those of you here in the US that may be using Steel Design Guide 11 or ATC Design Guide 1 might recognize the equation in the lower left, which is a acceleration over gravity ratio. And actually this equation is derived from the steady state equation on top, and it makes some assumptions. It assumes that the mass is equivalent to half of the mass in the structure. So in other words, you'll see the weight term in there, which cancels out the 2 term in the denominator, and then we have the gravity term, which is also introduced because we're converting from mass to weight. But essentially we're applying this for the simply supported beam, where we knew that the modal mass was 1/2 of the total mass. And so that's the assumption that's made here in this equation. You'll also see that the only real terms in here, in addition to damping, is the natural frequency of the structure. And so we only get one natural frequency, even no matter how many modes we have, and the assumption here is that the predominant vibration frequency is going to be the fundamental frequency. And that may be true, but it may not be true for irregular structures. So while this equation is likely applicable to simply supported beams and is definitely applicable to a single degree of freedom system, it is not applicable to more complex situations. And so most concrete floors, this will not be a good equation to use to calculate vibrations. So luckily there's a better way. If we look at to the right side of the red bar, we see a much more complex solution, but it's also another closed form solution that is more applicable to irregular structures. And if you'll just take a quick look at a couple of points with these equations, I'm not going to go into too much detail on them, but you'll see that there is a forcing frequency over a modal frequency, so we can now talk about calculating a frequency for any mode, not just the fundamental mode. And we can also calculate for different harmonics. So we're looking at not just a single forcing frequency, but usually up to 4 harmonics of that frequency. So like we showed in the dynamic loading slide a while back, where we were using a Fourier series to come up with our design dynamic footstep load, we were combining 4 harmonic loads. And so we can do that here. We can calculate a response, an acceleration for each harmonic and also for each mode. So it's very robust. And then we basically combine the results. So we sum the results down there near the bottom for each mode. You can see the summation here, where we're looking at the summation for each mode for an individual harmonic. So we sum those together to get a harmonic load. So we'll have 4 of those altogether because we're using the first, second, third, and fourth harmonic calculations. And then the last step is to combine them together, and we do that using square root of sum of the squares. The reason why we need square root of sum of the squares there is because we don't have the phase information about those different harmonic accelerations. We know the peak acceleration, and that's an accurate value, but we don't know the phase relationship between them. So there is a bit of approximation there, and that goes into that calculation, but that is how we can combine those four harmonic accelerations into one single acceleration. And again, that's our peak acceleration for the floor at any given node. I want to note that in the equations above, you'll see that the mode shapes occur in that equation, and you see two different terms for the mode shape. The mode shape is the mu value in the top equations there. And so you see a mu r comma m and a mu e comma m. So the r is the calculated response node or location, and the E is the excitation location. So we can actually calculate a response at a different location than we apply excitation. So this is very flexible and robust closed form solution that we can use to solve irregular structures where we're exciting the structure anywhere we want, and we can calculate the response anywhere else in the slab. And coincidentally, those can also be at the same point. So we use the same value of mu, which again, recall that mu is the value of the mode shape at a particular point, and that is a unity normalized mode shape. So one other thing that we can do with this sort of approach, because we can calculate any footstep frequency and not just dialed in on the fundamental frequency, we can calculate the response for a whole range of frequencies and create a plot like the one we see here, where we can look at which footstep frequencies generate the highest response. You'll notice that this plot has lots of peaks and valleys. The peaks are going to be located where the applied footstep frequency or one of its harmonics aligns with a natural frequency of one of the modes in the floor. And so we'll see that we also have these peaks of different magnitude. If we start by looking at the one at the far left, which is around 1.2 hertz, most concrete structures are not going to have a natural frequency that low. So it's likely that this response was caused by resonance with one of the harmonics. In fact, the fourth harmonic of that frequency is 4.8 hertz, which might align with near the lowest frequency, natural frequency of the floor. And so in that case, if you recall, when we're applying dynamic load factors, the higher the harmonic that we're calculating, the lower the dynamic load factor. So that would explain why the responses get higher as we travel further right on the plot, because the lower level footstep frequencies are likely only aligned with higher harmonics, whereas we move further to the right, our lower harmonics might actually be aligning with natural frequencies in the floor, and those lower harmonics have higher dynamic load factors. You'll notice that this plot is plotting acceleration. Oftentimes, resonant response is measured in acceleration. In fact, the equations we showed in the previous slide just measure the acceleration on the floor. So you'll see that we can look at vibration and measure vibration in terms of acceleration or velocity. It can be done either way. And we'll look at that a little closer later. But in the case of resonant response, we're normally calculating acceleration. You'll also notice that there are two plots shown on this graph. One is for the closed form solution, the blue line, and those are for the equations we showed on the previous slide. And the red line is actually for a full-blown dynamic modal analysis. The modal analysis does not suffer from the lack of phase information like the closed form solution does. So the modal analysis is going to be more accurate for that reason. So you might ask, why don't we always just use modal analysis? Because it's very, very time consuming. And so you'll see that the results from the two plots are very close. So the closed form solution, even with its approximation using the square root of sum of the squares to combine the different harmonics, is still a very accurate solution. And it's much faster. So it's generally suitable for day-to-day design. The resonant response we just looked at is generally applicable for lower frequency floors with a fundamental frequency less than about 10 to 15 hertz. So when resonance is possible, that will generally dominate the vibration response. However, if we have a higher frequency floor where the fundamental frequency is higher than that 10 to 15 hertz, we may have a vibration response that's dominated by impulsive response. And if you recall, an impulsive response is one where the vibration dissipates essentially before the next footstep is applied. So if you look at the diagram here, this is a plot for a walking frequency of 2 hertz. You'll see that by the time we get to a half a second, which is when the next footstep will be applied, that the vibration response is effectively diminished. So there is no buildup of vibration like there is with resonant response. So we're able to calculate this response as if it were just a single heel drop or a single footstep. We do this by calculating an effective impulse using the walking frequency and the natural frequency of the floor. And then we can use that walking frequency in the next equation to calculate a modal velocity for each mode. And we can do that by using the mode shapes for a unity normalized mode shapes. And we can apply an excitation location and calculate the response at any location we like. And for that, we can calculate a velocity for each mode. Using that modal peak velocity, we can use the next equation to calculate a velocity with respect to time. So that's essentially a time function that is using that peak modal velocity that we calculated in the previous equation. And then from that, we can build up the response of all the different modes. So the last summation there, the V sub t, the V as a function of t, is just a summation of all the different modes of the modal velocity with respect to time. So once we've calculated a velocity with respect to time, and we can plot that, which is what we're looking at in the plot here, we're going to want to compare that against some threshold value. And so when we have a impulsive response here, which has a high peak that diminishes quickly, that single high peak is not likely to disturb either occupants or sensitive equipment. So we want to try to use some sort of averaged value in that comparison. And that's what the bottom value in the lower left-hand corner there is, the V RMS. RMS stands for root mean square. So essentially we're taking the square of the velocity plot and we're integrating that over a particular time period, in this case over one footstep, and then we're taking the square root of that. So it's the root mean square. It's effectively an average of the velocity over a period of time, and that gives us a more predictive response that can be compared to some threshold value that's less sensitive to large spikes in the plot. And we can do the same thing with acceleration as well. We can do root mean square acceleration, which is often used to compare against acceleration thresholds, as well as the velocity root mean square value. Okay, now that we understand how to calculate an acceleration for a resonant response and a velocity for an impulsive response, let's take a look now at how we determine whether those values are within acceptable limits. So we need some sort of criteria to compare those calculated values against. What we're looking at here is a base curve for acceleration, and this basically, this red line in the curve represents the level of vibration based on acceleration that is just perceivable to humans. So this is at the threshold of human perception. And you'll notice that this is a root mean square value like we talked about in the last slide, and represented as a function of percentage of gravity. So you might ask why this threshold gets lower in the 4 to 8 hertz range, and the reason is that our bodies also have, and our internal organs also have, natural frequencies. And so there are frequencies that our bodies will be excited that are more susceptible or perceptible than other frequencies, and that's the reason why this curve has this particular shape. And we can also create a curve like this for velocity as well, so we can also create a threshold curve for either velocity or acceleration. But I want to introduce a new term here, which is called a response factor. And a response factor is simply a multiplier on this baseline curve. So again, this curve represents the level of human perception. So any point along this curve would represent a response factor of 1. If we generated a response factor of 2, that would represent a level of acceleration or velocity that was twice the level of human perception. So it just gives us some means to give a quick value without needing to know exactly what the acceleration thresholds are or what the velocity thresholds are. And it allows us to sort of compare results that are calculated using velocity and acceleration in an apples to apples fashion. If we convert them to this response factor, then we can compare them directly. And so it just gives us a simple means to understand a relative level of vibration with respect to the level of human perception. We can use this to generate some different thresholds. So you'll see here, and this is from the design guide from the Concrete Center. And so you can see that we've got this range of response factors in the second column. And so we can use these response factors to determine the thresholds that we want to use for different situations. So for instance, a response factor of 8 here we're showing for a workshop. So this is going to be a very perceptible vibration. It's 8 times the level that's just perceivable to humans. But this may be appropriate for workshops or other non-sensitive areas. So a high response factor threshold like that might be acceptable. In offices, a response factor of 4 might be suitable, where the vibration is actually perceptible, but it's not to the point to where it's going to disturb people working in an office. If we get to a response factor of 2, that's going to be above the level of threshold of perception, but still barely perceptible, and that might be appropriate for sleep areas, residential areas, and computer equipment. And if we have like an operating room in a hospital where people are going to be sensitive to vibrations, we want to limit the response factor to something smaller. So in that situation, a response factor of 1, which is just at the threshold of perception, might be suitable. And this also might be suitable for low sensitivity equipment or sensitive sleep areas. When we start getting into the bottom half of the chart, where we're looking at the VCA through E, we're generally dealing with sensitive equipment there. So those response factors are going to get even smaller. And you can see some examples that might be suitable for each category. So VCA, you're looking at microscopes that are with 100 times magnification, all the way down to the bottom where we're dealing with VCD, where we're dealing with electron microscopes and really demanding equipment. And VCE is the most stringent category we're showing here with a very small response factor, which is for the most demanding equipment, but that also might be very difficult to achieve. So by calculating accelerations and velocities and then converting them into response factors, we can sort of envelope for a floor the maximum response factor at any given location. We can create a plot of all of those and get a quick understanding in one single plot what the most susceptible locations are at any given floor. And we'll look at that in just a few minutes in an example. At this point, we've gone over very briefly how to calculate the vibration properties of a structure, how to calculate the dynamic response for resonant and impulsive responses, and also how to determine a threshold to compare those calculated responses to. But the question becomes then, how do we go about day-to-day design? Because we've looked at very simple situations and we've looked at some more complicated equations that would apply to irregular floors, but how do we apply those in our day-to-day design? And typically what we'll be wanting to do in our day-to-day vibration assessment is to calculate the initial vibration properties, which are the frequencies and mode shapes. We will want to calculate the resonant response to footfall, the impulsive response to footfall, and then evaluate those calculated responses against some appropriate threshold. So we'll take a look now at how we can do that using RAM concept and accomplish all of this very quickly and easily. So I have a model here in RAM concept that's already been generated, and we can take a look at the structure here. This has a flat plate slab with some stiffener beams underneath along the column lines, with some columns and walls above and below the slab. And so once our model is generated, doing the vibration assessment is extremely easy. All we have to do is click the Calc Vibration Analysis button on the toolbar, and RAM Concept will start the analysis. And the first thing it's going to do is solve for the frequencies and mode shapes, and again that uses the eigenproblem, where the eigenvalues represent the frequencies and the eigenvectors represent the mode shapes. So once that's finished, we're able to go to the vibrations folder, and we can look at some of the mode shapes that were calculated. So this is the first mode shape. You can see it's 6.9 Hertz, and it's predominantly one bay that's active here, although you can see that some of the adjacent bays also participate. And we can actually animate these plots as well and see them in motion. So we'll do that quickly here. And we can see what this mode shape looks like. Again, you can see it's dominated really by that one bay. And we can look at the first few mode shapes, and very similar, we've got this dominated by one bay. These are all slightly different frequencies, so in order to capture the appropriate behavior in each one of these bays, we need to take into account the frequency of the mode where that bay is most active. So it's important that we calculate all these different modes, or we might miss the predominant behavior in a particular bay. Again, we're up to 10.6 Hertz here, and we've got, again, just mostly one bay active here. And then when we get up to mode shape 6, we start to see a little different behavior. Here we've got a number of modes, or a number of bays that are active here, and we'll animate this one so we can see it in motion. But we see a bit of a checkerboard pattern, but there's a significant amount of participation in a number of different bays here. We can go look at the table for the mode data, and we can see that our fundamental frequency is about 6.9 Hertz, and it looks like the first 8 modes are probably all subject to resonance. We definitely need to do a resonant analysis on this slab. In fact, it's already been done. We'll look at the results in just a minute. But again, we can see that these modal mass fractions are all pretty small, and that's because we only have predominantly one bay that's active in the participation of each mode. But again, that also makes it important for us to make sure we analyze all of these modes that could be potentially subject to resonance. So to go look at the results of the resonant and impulsive analysis, we can look at, we have a root mean square acceleration plan, and a root mean square velocity plan, and a max response factor plan. So these are all envelope plans if we want to look at accelerations. And again, remember we're calculating the accelerations for the resonant response and predominantly working with velocities for the impulsive response. But if we look here, we can see a contour plot of the maximum acceleration at any point in the slab, which is very useful. It very easily lets us pinpoint where the problem areas might be. And you see the units here are meters per second squared. We can draw section cuts through here to see what the values are at any point in the slab. And what's happening here is we're treating each finite element node in the model as an excitation node, and then calculating the response everywhere else in the slab. So we're really getting a really envelope behavior of the entire slab. So each node in the slab is in turn being excited. So rather than someone walking across the slab, this is probably more analogous to someone jumping up and down at a single point at a particular frequency. And we'll look in a minute at what the properties are that go into this calculation, but we'll see that we're also considering a range of walking frequencies as well. In fact, let's take a look at that now. So if we go to Calc Options and go to the Vibrations tab, let's take a look at some of these settings here and what they might do. This is just the number of modes we're calculating. You really want to make sure that if you have a lot of low frequency modes that you're calculating enough modes where you capture all the resonant response. So that's important. 100 modes should normally do that fairly easily. There's a dynamic concrete modulus factor, and this is really just to account for the fact that in vibration or dynamic calculations, the modulus of elasticity of concrete is typically higher than it is in a static. So it's just a modifier, and 20 to 25% increase here is a typical value. So 1.2 is a good value for that factor. We have the opportunity to turn on or off whether we do the footfall analysis. So if we just wanted to look at frequencies and mode shapes, we could turn this off, but generally you'll be leaving this on. And we can set the range of footstep frequencies you want to analyze. So we want to basically consider anything that might be possible. So 1.5 to 2.5 is a pretty reasonable range of normal walking frequencies. And so we will also consider anything in between. So this is a minimum and a maximum. And we're going to calculate everything that could be significant in between. If you recall that plot we did with the resonant response where we were looking at those spikes at particular walking frequencies, that will all be considered in this calculation. We also have a damping ratio, which, if you, again, remember that this is a percentage of critical damping. So, and this is actually just a fraction ratio, not a percentage. So 0.03 represents 3% of critical damping here. And we can also choose whether we want to calculate resonant, impulsive, or both. And I generally recommend leaving on both. It doesn't generally take much longer to do both calculations, and that way you capture both responses, and all of the plots represent an envelope of both sets of results. So a couple other things that are notable here. For the resonant response, we can set the maximum natural frequency we want to consider. This is not likely to have much influence over the calculations. It might make them a little faster. It just excludes the higher frequency modes from the resonant calculation. And we also can input the static weight of the person. So this is the static load that will be used to calculate the resulting dynamic loads. And the other option we have are using a simplified calculation, which is actually the more complicated closed form solution we saw earlier in the presentation. It's called simplified here because it's not a complete modal analysis, but it is much faster than a modal analysis. And as we saw in those comparison charts, it's also very accurate. So this is the default calculation mode in RAM Concept that is used for the resonant response calculations. But in RAM Concept, it's also possible to do a full-blown modal analysis. And then we also have a little bit of control over what we're setting for the excitation nodes as well as the response nodes. So in addition to acceleration plots, we can also look at velocity plots. And these are also contour plots that represent the envelope of the solution at every node in the structure. And so one thing to keep in mind here, though, is that for the resonant analysis, we're only calculating accelerations, so that the velocity plot here will not include the results of the resonant analysis. And there was a warning that was displayed right after the calculation to that effect, just to remind you of that. So when we're dealing with accelerations and velocities directly, we need to be a little bit careful to make sure that what we expect to be included in the plots and what we're comparing against thresholds is appropriate. However, that's also another good reason to perhaps work with these response factors, because with the response factors, we calculate a response factor from the accelerations for the resonant analysis, and we calculate a response factor from the velocities with the impulsive analysis, and then they all get enveloped into this plot. So the response factor plot always includes the results of both analyses. And if you recall, a response factor of 1 basically corresponded to a level of vibration that was just perceivable to humans. And so in this case, we can see that we've got a maximum of close to 7. So we've got 7 times that amount in these red areas. But I think you should be able to realize the power of what we're looking at here. In one single plan, we get a snapshot of all the most sensitive areas in the entire slab. So these red areas that are above about 6.3 are the most vibration sensitive areas in this plan. Everything that's in the purple is fine. It's below 0.7, so it's very low response factor. And we can actually change these values, we can change these ranges to hone in on, if we're interested in those really small sensitive equipment ranges, we can change these ranges of these plot to represent something smaller if we wish. So I want to show a couple other small features that demonstrate the power and flexibility of RAM concepts implementation. Let's say, for instance, in this case, we're showing a really sensitive response here, but that's also considering that we're exciting it here. If you recall, the default implementation or the default calculation calculates every node as an excitation node. But let's just say we have a corridor going through the center of the building here, and that's really going to be where most of the walking takes place. So that's really the only area we want to consider as an excitation area. So we can actually draw the excitation areas where we wish, and then only those areas inside that shape will be considered for excitation. So if we had a corridor here through the center of the building, and we said this is all I really want considered for excitation. This is a residential room over here, and I don't expect a lot of heavy walking and footsteps, so I don't really want this to be considered as excitation. So we can simply rerun the analysis here. Now we can go back and look at the response factors, and you can see that we still get a fairly large response in this center because that was there anyway when we were exciting these nodes that we're considering in this corridor. But in this room over here, you can see the response is very much smaller because we're not exciting this node over here. We're still considering it as a calculation. We're still considering and calculating the response here, but we're only considering the response here from exciting the areas inside this polygon that we've just drawn. So this really gives you flexibility over what you're considering and how you're considering it. We can also define additional mass that goes into the calculation. This will primarily affect the calculation of the frequencies and mode shapes. But in this case, the self-weight mass of the structure will always be considered automatically in that calculation. But we can define superimposed loads if we've got permanent mass that's going to be on the floor that we want considered in the vibration calculation. We can add additional loads that are either area loads, line loads, or point loads, anywhere we want on the slab. And those will be considered then in the calculations. So the power and flexibility of RAM concepts implementation should be evident here. You can see how easy and quick it is to do an assessment of a concrete floor vibration, and we're really not making any leaps or big assumptions that are going to cause these results to be very approximate. We're using that approach, the robust closed form solution approach, that gives us very good predictions of vibrations for irregular concrete floors. The last topic I want to discuss today is the effect of post-tensioning on vibrations. And first I want to point out that I'm not an expert on this subject, but I have done some research and I will report my thoughts. And there does appear to be some degree of controversy on this particular topic. So I encourage you to do your own research and come to your own conclusions on this topic. I think when we talk about post-tensioning, it's also important to bring cracking into the mix. And some of the research that I've found indicates that cracking is really not that significant in vibrations until the reinforcement starts yielding. So in that case, in most service conditions, the effect of cracking on vibrations would not be that significant. So other researchers, and intuitively you might think that cracking would reduce the stiffness and thus reduce the frequencies of the modes. And so if that's the case, then we might expect that post-tensioning would have some influence over that, because once cracks occur and that reduction in stiffness occurs, you could introduce some post-tensioning that would close those cracks and sort of reinstate the gross stiffness of the slab. So from that regard, post-tensioning would only be beneficial if there is going to be cracking in the slab and you are considering that cracking is going to influence the vibration properties. With that said, there's some other research I've read that indicates and talks about a behavior called compression softening due to post-tensioning, which would be analogous to buckling. So the frequencies would be reduced as the post-tensioning is increased to some large level due to a buckling effect. And so in that scenario, the post-tensioning could have a negative effect on vibrations. It could actually reduce the stiffness instead of increasing it. So I'll leave the decision as to whether or not to include cracks up to you. But if you use RAM concept for the vibration calculations, just know that the post-tensioning will be included in those calculations. Before we close, I want to show you how you could consider the effects of cracking in the vibration calculations in RAM concept, and also potentially the beneficial effects that post-tensioning would have on preventing cracking. So if we go back to the criteria and calc options selection and the vibrations tab, we'll see that there's a stiffness matrix option, and the default selection there is the global stiffness matrix, which would not include any cracking or the effects that post-tensioning would have on cracking. But if we wanted to include those effects, we could simply select a load history step that would generate the cracking loads that we want to consider. So if we select that, run that load history, which does take into account cracking and would take into account the beneficial effects that post-tensioning would have on cracking, then that would be included in our subsequent vibration analysis. With that, I will conclude today's presentation. I hope you found the information useful, and I want to thank you for attending.